These are notes on properties of acids and bases. In your book, Acids and Bases are chapter 18. So today we're going to look at 18.1, but then we're also going to go back to 9.4, which was the chapter on naming. And at the time we skipped over naming of acids and bases, and so now we're going to go back to that. So that's why 9.4 is thrown in here. So a couple general properties of acids and bases. So first we'll look at what they both do, and then we'll look at how they're different. So they both change colors with indicators. So an indicator is a chemical that changes color in the presence of an acid or a base. And so one of the ways we can tell how acidic or how basic something is by using an indicator. And some indicators are commercially made, but there's also a lot of natural indicators around us. So for example, I'm going to show you an example of how red cabbage, or some people call it purple cabbage, actually changes color in the presence of acids and bases. So we'll do some fun stuff with that. Both are also strong or weak electrolytes when aqueous. So you may remember all the way back to when we talked about ionic compounds, and that ionic compounds, when they're dissolved in water, they dissociate, they separate apart. So instead of being like NaOH, it's Na plus and OH minus. So strong acids and bases will completely dissociate in water. So their ions will totally come apart. So HCl is a strong acid. When dissolved in water, it's H plus ions and Cl minus ions completely. Weaker acids and bases will dissociate to some extent, but not completely. So vinegar, acetic acid, which is hydrogen with the acetate ion, some of it in water will be H plus and some will be the acetate ion, which is the negative ion, but then some will stay the compound together. And the same with bases. And then acids and bases can neutralize one another, or essentially cancel each other out. So some of you may have noticed when you've spilled acid this year, I'll take a bunch of baking soda, which is basic, and dump it on the acid, and it kind of fizzes up, but then that neutralizes it and it makes it safe to dispose of. So acids then are sour, so they taste sour. If you think of lemons, lemons are acidic. All citrus fruit is acidic. Actually, most fruits, if not all, are acidic. So apples are acidic. Berries are acidic. Pretty much any fruit. I don't know about bananas. I don't know. At any rate, but most fruits are acidic, and they don't all have a hugely sour taste, but that's a good indication of an acid. Whereas bases taste bitter. If you think of soap, soap is a good example of a base. If you've ever gotten like shampoo in your mouth as you're washing your hair or something, obviously I'm not assuming you're like gnawing on bars of soap, but it happens. And while bases do taste bitter and acids tend to taste sour, as a rule of thumb, it's never a great idea to taste things in the lab to go, oh, I wonder if this is acidic or basic. Bases also tend to be slippery. And then, so again, think soap. And then acids are corrosive, whereas bases are caustic. And it's funny because if you look up the definition of these things, they're actually synonyms of one another, and they both mean they eat away at things. But when we're talking about acids, we generally say corrosive, and with bases, we generally say caustic. And then later, we'll talk a little bit about pH and what the pH scale means and what those numbers are. But right now we're just kind of looking in general. All right, so there are different ways you can define acids and bases depending on how specific or general you want to be. Your book actually talks about 3 different ways. I'm going to focus on 2 here. So the first is the Arrhenius definition of acids and bases. And in this definition, acids contain hydrogen that yields H plus ions in aqueous solution. And bases contain hydroxide that yields OH ions in aqueous solutions. So pretty straightforward. If it's got a hydrogen that becomes H plus when dissolved in water, it's an acid. If it's got hydroxide, OH minus, that becomes OH minus ion in aqueous solution, it's a base. So in this example here, let me get a pen here. We've got HCl gas being dissolved in liquid water, becoming aqueous H plus and aqueous Cl minus. So we would say the HCl is a gas, an acid, because it yielded an H plus ion. Now, in reality, that H plus ion then interacts with the water and forms, remember water's H2O, an H3O plus. And this ion here, I'm going to attempt to write this, is the hydronium ion. Hydro for water. It's the hydronium ion. And that is worth mentioning because we're going to be talking, when we get to pH, we're going to talk a lot about the hydronium versus the hydroxide ion, because water itself will form some H3O, but then if it's forming H3O, it's got to also be forming OH minus. And so one of the things we look at with acids and bases is the concentration of hydronium as compared to the concentration of hydroxide. And again, we'll talk about that a little later. So then here we have KOH, potassium hydroxide. And in water, when it's dissolved in water, it forms the OH, dissolves and forms OH minus. So based on the Arrhenius definition, KOH, potassium hydroxide, is a base. Now, one of the things is I'm going to give you, so the Arrhenius definition is, I would say, the most simplistic. The reason we need other definitions is because it actually doesn't cover all bases. So, for example, ammonia, NH3, is very basic, yet there's no OH in NH3, so that's why it doesn't fit into this definition. But anything that's an acid or base based on the Arrhenius definition is an acid or base based on the other definition. So it's not like this is an acid here and a base there, with one exception, and that's water. Water can sometimes act as an acid or a base in any definition. So we'll look at that in a little more depth. So the next definition I want to give you is the Bronsted Lowry acid and base definition. And Bronsted Lowry definition includes things like NH3. So what do you do with things that are clearly acidic or clearly basic, but don't have an H plus ion or an OH minus ion? Well, those don't fit into that definition, so we need to broaden. I guess you could say Arrhenius is the least broad, and then Bronsted Lowry is a little broader, and then Lewis acids and bases are even broader. We're not going to look at Lewis. We're going to stop at Bronsted Lowry. So in Bronsted Lowry acids and bases, acids are hydrogen ion donors, and bases are hydrogen ion acceptors. And a lot of people will memorize this acronym, BAAD, bad. And that stands for bases accept, acids donate. And when we're talking about what they're accepting and donating, that's hydrogen ions. Now, just so you know, if you go further in the book and you do read about Lewis acids and bases, it's just the reverse, that Lewis acids accept electron pairs and Lewis bases donate electron pairs. As I said, we're going to stop here as far as the scope of this course, but it is in the book, and so I wanted to bring your attention to that. And that's an even broader definition. And it doesn't contradict this at all. It's just talking about a different donation and accepting. The other thing is, when we talk about hydrogen ions, if you think about hydrogen, right? Hydrogen is one proton and one electron. You can say one P plus. So a hydrogen ion is simply a proton. And so a lot of times we'll talk about acids as being proton donors and bases as being proton acceptors, and that's because a hydrogen ion is just a proton. So let's take a look at this equation here. Here we have ammonia that I was talking about earlier, and I will just tell you that ammonia is a base. Okay, we'll get into the details of that later if you want. But for right now, accept that it is a base. And when we dissolve it in liquid water, we get NH4 plus, and this is really more like this. I mean, the KQ of that is so large. And then OH minus. Okay? So it forms OH minus ions, right? So you think, okay, base, except that it's not the ammonia forming the OH. It's actually the water forming the OH, because the water is giving the hydrogen to the ammonia. So as you can see, the ammonia is getting a hydrogen ion, which then actually makes this the ammonium ion. This is then an ion. And the hydrogen, or the water, so the water is donating and the NH3 is accepting that H+. So we would say that the NH3 is a base because it accepted a hydrogen ion or a proton, and that the H2O is an acid because it donated a hydrogen ion or a proton. So that's a little more general definition of acids and bases, not just based on their whether they have an H plus that becomes an ion or an OH minus that becomes an ion. So then I do want to talk briefly about naming acids, and this again is in 9.4 of your book. Naming bases is just, bases tend to be, except for things like ammonia, tend to be ionic compounds with OH minus ions. So you just name them the way you would name any ionic compound. And of course there are definitely like special names for different acids, like, you know, we talk about citric acid or salicylic acid. You don't need to worry about those. But there are some rules for some general acids. So you want to look at the anion in the acid. So remember, anion is the negative ion. So if you look, for example, at HCl, the negative ion chlorine, we would say is the chloride ion. So if the anion ends in "ide", then you begin the acid with the word hydro, and the anion suffix changes to "ic", and then the word acid is put on the end. General rule of thumb, as you'll notice in all of these, is that the word acid is put on the end. So chloride ends in "ide", so we put hydro in front. We change the "ide" to "ic", and then we add acid, so hydrochloric acid. If the anion ends in "ite", if you remember, SO3 is sulfite, then the anion changes to "us", and the word acid is put on the end. So this is sulfurous acid. If the anion is "ate", and if you remember, SO4 is sulfate, the anion changes to "ic", and the word acid is put on the end. So very similar to "ide", except we don't start with hydro. And so this is sulfuric acid, sulfuric acid. Please feel free to add any questions to the YouTube comment section, or you are welcome to ask in class tomorrow. Have a good day.